Don't you, if you are talking, you are muting yourself.
Oh, I'm sorry. I'm sorry. Can you hear my voice?
No, yes, I can hear you now.
Okay.
I hear you too.
Okay, yeah, sorry. Yeah, let me again, describing these problems. So in this lecture, we're going to study the field behaviors in hollow metallic waveguide on the right-hand side here. The left figure describes the coaxial waveguide consisting of two metallic structures disconnected. We know that this waveguide can support TEM waves in which electric field and magnetic field are perpendicular, and also they are perpendicular to the propagation direction. On the other hand, this right figure describing hollow metallic waveguide has just one metallic wall. This waveguide cannot support TEM waves. Instead, it can support TE, transverse electric, or TM, transverse magnetic mode. And in this lecture, I'm going to focus on describing TEZ mode, which means that transverse electric Z. Z means propagating into Z direction. Okay. And at the end of the last lecture, we studied how to construct the solution of this TE mode. TZ means that electric field does not have longitudinal component, in this case, Z component, so that by Maxwell's equation, we can construct electric field solution curl of the Z components of vector. In this case, it turns out that this is gonna be the Z component of magnetic field. That's why we add some subscript at H here. This is scalar potential. And if we, this electric field is solution of the Helmholtz wave equation. Beta here is the wave number of this mode. So omega square times mu epsilon. We're gonna assume that inside of metallic waveguide, just vacuum. and the sourceless, there's no sources, so that just equal right hand side becomes just equal. And then if we plug electric field solution to the Helmholtz wave equation, we obtain this equation, and this scalar field should be solution of the Helmholtz wave equation as well. And we know that this wave is propagating to the z direction, positive or negative direction. And we're gonna do so-called separation of variable, which is widely used to solve the partial differential equation. So that the contribution of z is just the exponential function describing the traveling wave. And the other part, actually this is the transverse part. Again, the scalar potential, which is a function of the RS. RS kind of position vector over this cross section. I mean, RS is just the position vector of this. If we describe in Cartesian coordinate, it's going to be XY. And also due to the boundary condition of electric field, we studied that this transverse part of the scalar field should satisfy so-called Neumann boundary condition, okay? Which is the normal derivative should be 0. So that we need to solve this equation. This Laplacian operator sub S means that Laplacian operator over this cross section, the transverse plane. So if we know this function, then we can know the scalar field. Eventually, we can know the electric field solution. And then magnetic field solution can be obtained by using the Maxwell's equation. So we're going to deal with two specific types of waveguide. First one is the rectangular waveguide, and the other one is the circular waveguide. And then we're going to explicitly solve this transverse Helmholtz wave equation. Okay. Again, the transverse Helmholtz wave equation was given in this way. Equals to 0. Okay. This is just a partial x squared and a partial square partial y squared, so that we need to solve this equation. Okay. So what was the from the advanced engineering mathematics course, we know how to solve these partial differential equations in Cartesian coordinate. In this case, the general solution of this scalar field should be using separation of variable. For example, just a linear combination of cosine and sine function. Beta x. This is the x contribution, and y contribution. Okay. So this is the general solution. On top of this, to have the unique solution for this structure, we need to apply the boundary condition. Okay. The boundary condition was given by the normal derivative should be 0. So if we draw this transverse plane, gonna be y, a, b over the boundary. So in this case, the boundary is gonna be these metallic walls. So this is when y equal to 0, and this is x equals to 0, and this is x equals to a, y equals to b. Okay. Yeah, I'm gonna skip the details of math. However, by applying these two boundary conditions, we can figure out that the solution should be like this form. Just the arbitrarily constant times cosine beta x and cosine beta y, okay, by using these two boundary conditions. And also, then let's apply this boundary condition on this surface. Then first this surface, okay. Then in this case the normal derivative should be partial x. Okay, then if we apply the partial x, hs, when x is equal to a, just applying plugging this expression to here, then it's gonna be proportional to sine beta x and cosine beta y. Just differentiating this cosine function. It should be 0 when x is equal to a. So in order for this equation is to becomes to 0, we need to make sure that beta x a, this argument of cosine function, should be integer multiple times pi, so that the beta x is gonna be m pi over a. For m, the integer m here, okay. Likewise, we can apply this boundary condition of the fourth wall when y is equal to b. In that case, we can follow this similar procedure. Then we can obtain the beta y is gonna be another integer multiple times pi over b. So our solution is gonna be some constant and the cosine m pi over a x, and the cosine b and pi y. However, then let's consider this case when m and are equal to 0. Then this field is just a constant, okay, not a function of x and y. So that except for h z field, all the other electromagnetic fields are going to be 0. And it turns out to be this mode is just the electrostatic solution. So that is not the solution of our interest. So we exclude this case when m and n are equal to 0. So only solutions of our interest is that when m start from 0 and also start from 0, but except for this case, okay. So this mode is called the TEMN mode. Then our wave number was given in this way. Beta s squared. Beta s squared is the beta x squared and beta y squared. It was m pi over a and n pi over b, so that actually the beta is the wave number, which is omega squared mu epsilon. So that if we manipulate this dispersion relation in terms of bz squared, it's gonna be beta squared. Maybe better to exclude the squared term. Just beta squared was the omega squared mu epsilon minus m pi a squared minus n pi b squared. Okay. So actually, it was the propagation constant along the z direction of this mode. So we can know that if omega is less than the omega less than the 1 over square root of mu epsilon and n pi over a squared and pi b squared, then inside of the square root is going to be negative value. And that means that this is going to be imaginary. That means that the mode is not propagating but attenuating while propagating. So that's not the propagating mode. So in order for this TEMN mode to be propagating, we need to make sure that inside of this square root is positive, so that this beta z is the real number. That's the guidance condition of this TM mode, so that this omega should be greater than the 1 over mu epsilon and this one. So when omega is equal to this value, actually this value is called the cut-off frequency. Okay, so as long as omega is greater than the cutoff frequency, this TEMN mode can propagate inside the waveguide. Okay. So any other questions so far?
Would it be possible to use the waveguide as a filter then?
By using this effect, I mean oscillating some field below the wave cutoff frequency. Yeah, better to discuss this figure. I'm not sure this physical property of TE mode can be used for filtering application, but I think, for example, the MN indexes increases, the cutoff frequency also increases. So in the in this way rectangular waveguide, the TE10 is the lowest mode which can propagate inside a waveguide. So if we excite some sources below, for example, 1.5, I mean, in this case, 1.5, yeah, this is just a symbolic expression for frequency. if we excite source below 1.5, all the other higher order mode are naturally filtered out. We can just excite the T10 mode. So that's kind of filtering mechanism, but in order for us to filter out some specific bandwidth or something like that, we need to introduce another kind of filter devices. But it's not enough to filter. I mean, this attenuation mechanism is not proper for filtering out the specific bandwidth or something like that. Actually, this is the TE-MN mode closed form solution. We know that the transverse scalar field takes the form of the cosine and cosine function, but you can also find the TM-MN mode by using the similar argument. In this case, the H field should be given by the curl of the Z component of the scalar field. And the boundary condition is going to be just a Dirichlet boundary condition, which means that each transverse part just a zero over the surface of the transverse plane. Okay. And then in that case, ES transverse field solution given by kind of constant and sine and beta x and sine beta y. You can also find this cutoff frequency of this mode. Also, it's going to be n pi over n and n pi over b. But in this case, m n should start from 1. Otherwise, the field solution becomes 0, which is trivial solution. Okay, so lowest mode is the TM11 mode. On the other hand, the TE case, the lowest mode, which means that the mode has the lowest cutoff frequency, is going to be TE1, T01 mode. I mean, in RF engineering area, it's customary to set the lateral dimension is larger than the vertical dimension, so that the T10 mode is the lowest mode that we can excite. Yeah, so let me then draw this field, bouncing wave picture. So we know that this kind of wave is propagating wave, propagating to positive z direction. On the other hand, cosine beta z is kind of standing wave. Okay. Mathematically, by Euler formula, it is a superposition of two propagating waves, which means that two propagating mode result in this standing wave. So in our previous study, the transverse field of the TE mode was kind of cosine beta x and cosine beta y. So while propagating into z direction, this kind of field profile can be interpreted as bouncing wave picture. So meaning that the waves propagating plus x or plus y, they're bouncing around, bouncing inside this metallic wall so that they form these standing waves. Okay, that's the physical picture of this transverse field profile. So this is the dispersion relation of the TE mode inside the waveguide. Okay, our dispersion was given by omega squared mu epsilon was m pi squared and n pi b squared and plus beta z squared. So this figure illustrating this dispersion. I mean, in this case, this was k squared. This was k z squared. And this is the light line. I mean, the waves, electromagnetic wave in the free space. And let's look at the TE10 mode, which was the lowest mode inside this rectangular waveguide. It cannot propagate before this cutoff. After cutoff, as frequency increases, it takes like this line of dispersion. You can see, you know that the you can see that as frequency increases, its dispersion converges to the light propagating in the free space. So as frequency increases, this TE10 mode behaves like waves in the free space. And also, these are kind of order of the cutoff frequency of various mode. As you can see, TE01 mode is the lowest mode, and there are higher order modes appearing as the curve frequency increases. Again, let's say before the frequency 2, below the frequency 2, we can only excite the T01 mode. On the other hand, below the 3, we can excite many various higher order TE or TM mode.
I have a question.
Yep.
What is this? Those numbers 2 and 3 and 4 on those graphs on the left, are they normalized frequencies? And if normalized, over what, over which frequency we normalize them?
Mm-hmm. Yeah. So this MN index is the eigenvalue of the beta x and beta y. Actually, beta y was given by m, integer m, times pi over a, and beta y was integer n times pi over b. And you can see that this was the cutoff frequency. So let's say if m is 1 and n is equal to 0, then the cutoff frequency is, I'm gonna, this is just the speed of light, c times pi over a squared for a fixed value of a and b, just the geometric parameter. It turns out that as this m and mode increases, for example, m and r equal to 1, then the cutoff frequency is going to be pi over a squared and pi over b squared, which is greater than the former case. M is equal to 1 and n is equal to 0. So this is kind of index of mode, just the integer index. And these integer indexes increase and the cutoff frequency increases because the inside of square root is larger than this left one. So that means that if we increase this index mn, then each cutoff frequency also increases. And for example, TE11 mode, it can propagate above each frequency, cutoff frequency, let's say 1, 1. Below this cutoff frequency, it cannot propagate, it's just attenuating. It does not something to do normalization or something, just the index of cutoff frequency. And that cutoff frequency is related to this geometric parameter.
I see. Thank you.
Okay. Are there any questions for rectangular waveguide? Okay, then we can move on the circular waveguide. Just the same procedure to obtain the closed form solution, but difference between the rectangular and the circular waveguides is that the shape of this transverse plane. In rectangular waveguide, the transverse plane was just rectangular, so the Cartesian coordinate is would be best choice for our study. On the other hand, in the circular waveguide, due to its shape, circular shape, it's best to choose cylindrical coordinate. Okay, rho, phi, and z. So we can start just this transverse Helmholtz wave equation again. Again, TE Z mode. Sorry. In this case, phi and low and phi. Okay. So if we explicitly write the this part, the cylindrical coordinate system, it's gonna be 1 over rho. More complicated, just the Laplacian operator in the cylindrical coordinate system. Plus beta squared and the phi, I'm sorry, psi rho and phi is equal to 0. So in our previous study, I mean the Cartesian coordinate, the general solution of this field was like triangular or trigonometric functions, cosine and sine functions. But in this cylindrical coordinate, do you have any idea of the general solution of this cylindrical partial differential equation? Okay. It turns out that the general solution can be given by just so-called Bessel function. Okay. Bessel function and just the trigonometric function over phi. This Bessel function describes the field profile over the radial axis, and then this is just the oscillating field along the azimuthal direction. And this is the general solution. Bn actually includes the Bessel function of the first kind and Bessel function of the second kind. This is kind of a standing wave form. Likewise, trigonometric function. The cosine and sine is kind of, let's say, this is the symbol of the trigonometric function. It is the standing wave form, but there is kind of traveling waveform here by using exponential function. On the other hand, the Bessel function, this is the standing waveform, and there is a Hankel function. This is Hankel function, first order and second order. it is counterpart of this trigonometric traveling waves, traveling waves of this Bessel function. Okay, so this is the general solution of this equation. So in order to find again the unique solution of this circular waveguide, we need to apply the boundary condition that was the normal derivative when rho is equal to a. The radius of this circular waveguide should be 0. Okay. I'm gonna skip the details of derivation. You can refer to lecture note and you can practice how to solve this partial differential equation. Then among the Bessel function of first and second and Hankel function, the unique solution is gonna be the Bessel function of the first kind. So the arbitrarily constant times Bessel function of the first kind, BSA, this rho, the exponential plus minus j n b. Again, n is the integer multiple related to the order of this Bessel function of the first kind. So if we apply this boundary condition, then the derivative of this Bessel function when rho is equal to a should be 0. Okay. Then if we make sure this argument of the derivative Bessel function such that this whole function value is equal to 0, then that's gonna be the eigenvalue of this TE mode inside the circular waveguide. Now let us describe how this Bessel function looks like. So this is the actually the J denotes the Bessel function of the first kind. Okay, it looks like this. This is the Bessel function of the first kind when n is equal to 0. So this is kind of x and y plane. It looks like a cylindrical wave. And if we draw just the radial profile of this function from 0 to rho, then it looks like this way. So this is again the radius, and this is the function value of the Bessel function of the first kind when n is equal to 0 or 1 or 2. Okay. So our boundary condition was this. I mean the derivative of the Bessel function. So this figure illustrating the Bessel function of, I mean the derivative of Bessel function when again n is equal to 1, 2, 3, 1 to 0. So if we look at the 0, then this and this 0 crossings make sure that this boundary condition. Okay. So this 0 crossing information is included in this table. So this is the case when n is equal to 0, this function, okay? So these values are 0 crossing, I mean this point, okay? So that our boundary condition was, for example, n is equal to 0 was this. So this is equal to 0, when beta SA, this whole argument is 3.4832 or 70616, something like that. Then our eigenvalue is gonna be A over 3.832, something like that. Okay. In the same way, we can find eigenvalue when n is equal to 1 for this TE mode. And the order of the zero crossing is indexed in this case n, meaning that when n is equal to 0, this is the first zero crossing, and this is the second zero crossing, and third and fourth. Okay, so that this mode is called a TE. N is equal to 0 and M is equal to 1. Just because this is the first crossing when N is equal to 0. Likewise, this is going to be TE 0, 2 mode. Actually, this is very complicated to read this table and what's the meaning of the zero crossing of the Bessel function. Are there any questions about this reading table and the meaning of this index of the circular waveguide?
So, so in the chart above the table, these are corresponding with kind of the first three columns of this table, right? Because you've got the J prime 0, J prime 1, and J prime 2. Those 0, 1, and 2, are those representative of the M or the N?
You mean this index?
Yeah, yeah.
This is the represent N.
Okay.
N, and this order for a given N, this is the given N when it's equal to 0, then the order of this zero crossing is indexed N, okay? So this is the, for example, J0, and this is M1, first zero crossing, and this is gonna be the second crossing, and the third and fourth and so on. And also, this is our beta S. Again, the dispersion of this mode was given by beta squared wave number omega squared mu epsilon was beta S squared plus beta Z squared. Okay, so if we plug I'm gonna denote this zero crossing is psi, okay, psi n. Then if we we can find the cutoff frequency such that the beta z should be positive value omega squared mu epsilon minus beta S squared, so that if we plug this expression, then it's gonna be omega squared at mu epsilon minus A, which was the radius of the circular waveguide, and zero crossing. MN zero crossing, sorry, this is not squared. This whole thing should be squared. So that in order for this beta z is positive value, our cutoff frequency, this subscript cut, C means the cutoff, TNM mode becomes 1 over mu epsilon and A chi n. Okay, this is the cutoff frequency of the circular waveguide. So that circular waveguide, the lowest mode of the circular waveguide is TE11 mode. Actually, that's because if we look at these zero crossings, I mean, if we look at this cutoff frequency increases as this value of zero crossing increases, okay? So that if we pick lowest value of zero crossing, that corresponds to the lowest, the mode which has the lowest cutoff frequency. That's called the lowest mode. So then what would be the lowest value of the zero crossing? This is the TE case, TN case. We can figure out that this is the lowest value, 1.841, due to the property of this Bessel function. It corresponds to n is equal to 1, and m, this is the first zero crossing, so that m is equal to 1. So that the lowest mode corresponds to TE11 mode. And the next higher order mode is TM01 mode, and so on. Again, this is the dispersion of the circular waveguide. This is the light line of the free space. You can see that lowest mode appears very first after the cutoff frequency, and higher order mode appears in order. By the way, we were focusing on this scalar field, right? Transverse plane. We studied how to find the closed form of this solution for rectangular waveguide and the circular waveguide by solving the transverse Helmholtz wave equation. Then we can construct the whole solution by using this equation. The electric field is curl of the z component of this HS, RS, beta plus minus beta z and z. And also the magnetic field by Maxwell's equations is going to be curl of E divided by j omega mu. Okay, so that we can construct the whole field configuration. For example, these are a set of plots illustrating electric and magnetic field configuration of each mode. This is for rectangular waveguide. This is the circular waveguide. So you can see this solid line represent electric field, and this dashed line is the magnetic field. You can see that the mode index, by the way, in rectangular waveguide, it was TEMN mode or TMNN mode. In circular waveguide, TENN mode and TMNN mode. Okay. So as this mode index increases, the field gets more oscillating. You can see that the field variation is much faster as mode indexes increase. In the same way in the circular waveguide. Okay. Any other questions so far? Okay. Then let's discuss about the metallic ohmic laws. Actually, these waveguide, hollow waveguide, are usually used for high power microwave engineering applications. That's because if we are operating a very high power signal, and then if we use a transmission line involving some dielectric material, this dielectric material has the voltage breakdown due to the operation of high power, so that we need to use the air, which has very high threshold of the voltage breakdown. So we are using this hollow waveguide. However, in microwave, the metal, previously we always assumed metal as a perfect electric conductor. That means that the conductance is infinite value. There is no loss. On the other hand, in practice, for example, copper and aluminum has some finite conductance value, so that we have some ohmic loss while operating those metallic hollow waveguides. So I'm gonna explain the brief mechanism of this ohmic loss of the metallic waveguide. We know that if we have some metallic surface here, the loss comes from the surface current, okay? And the surface current, in order for this current to be induced, we need to have the transverse magnetic field. You can check the boundary condition of the magnetic field. It's gonna be surface current. So if we minimize this transverse, by the way, this is X and Y. In this case, current is flowing to the X direction, and the magnetic field is along Y direction. So in order to minimize the loss, ohmic loss, we need to minimize the strength of the transverse magnetic field. So it turns out that the TE0 mode of the circular waveguide has the lowest amount of this transverse magnetic field. Okay, that's why this TE0 mode is widely used for high power microwave applications. And furthermore, if we increase the frequency, if we look at this figure, if we increase the frequencies, the loss is minimized in TE0 mode case. So following this, so Y is the kind of attenuation parameter, which is the function of this loss. So that's why we are using TE01 mode of the circular waveguide for various high power applications. The order is around the frequency to -3/2 in the rate of the this convergence. So actually the loss is directly related to surface current. So there are many clever strategies to minimize the surface current. For example, we can induce some surface roughness of this metallic waveguide, like in this way, so that the current, we can minimize the current flowing over the surface. That is the common strategy used in this horn antenna to minimize the ohmic loss, something like that. And also, the last topic of this lecture is about Quasi-Tem mode. So we have discussed hollow metallic waveguide that can only support TE or TM mode. On the other hand, in the microwave circuit, These micro strip lines are widely used, consisting of this metallic signal line and the ground plane, and they're insulated by dielectric material here. This is air and the dielectric material. We have studied that if we have a two metallic rod, then TEM mode can be supported in the air. TEM mode has the distinct property that its propagation constant should be same to the phase velocity of this medium. Air or homogeneous medium, epsilon mu, so that it's gonna be omega mu 0. This is one property. The other property is that electric and magnetic fields should be constant, and they are also perpendicular to the this wave number. If wave is propagating to the z direction, okay. Then I'm gonna prove that this structure, microstrip line, cannot support exact TEM mode, but it can support so-called quasi-TM. Looks like almost TEM, okay? Again, TM mode, its propagation constant is the phase velocity of this medium. Let's say this dielectric has epsilon 1 and mu 1. Air has epsilon naught and mu naught. The phase phase velocity of air is gonna be omega mu naught epsilon naught. This is propagation constant. This is gonna be omega and mu 1 epsilon 1. So if we assume that there is a TEM mode in air region and another TEM mode in this dielectric media, propagating with this propagation constant. Actually, this is not the metallic surface. This is metal, and this is the interface between air and dielectric material. But we can find that these two waves cannot satisfy the phase matching condition at this interface. Okay, that's because they are propagating with a different phase, wave number, propagation constant, so that these two TEM modes cannot be supported by this structure. But actually, the field supported this micro strip line looks very complicated. It cannot be derived by deriving the form of in the closed form solution. Very complicated. On the other hand, this micro strip line is operating at a very low frequency, meaning that the wavelength is very large compared to the size of this micro strip line, so that degree of the mismatch of phase is very small, so that actually this phase mismatching result in some EZ and HZ component. This is a zero direction, but degree of the mismatching is very small, so that this field values, longitudinal field values, also very small, so that the resulting field almost look like a TEM mode. And that's why we are using the transmission line theory that we have studied by defining voltage and current, inductance and capacitance. Transmission line theory to study this microstrip line. And also the same argument can be applied to the coplanar waveguide. Looks like this. In this case, we have three metallic structures and also optical fiber consisting of the cladding region and the core dielectric region having different dielectric material. We're gonna discuss the microstrip line later more in detail, but I just wanted to explain why this microstrip line cannot support exact TEM mode. Okay. I think yeah, we have 10 minutes more. So are there any questions for our today's lecture? Then let me just give you overview on today's lecture. So yeah, what we have done is to find the transverse field profile of the hollow metallic wave guide by solving this transverse Helmholtz wave equation for boundary condition. There are two kinds of mode this hollow waveguide can support. One is the TEZ mode and the other one is TMZ mode. TEZ mode should satisfy Neumann boundary condition, stating that each normal derivative is equal to 0. On the other hand, TMZ mode should satisfy Dirichlet boundary condition. Just the field is equal to 0 on the boundary of the transverse plane. So we have transformed this transverse Helmholtz equation, the explicit form in the Cartesian coordinate to study the rectangular waveguide. And well-known, the general solution of this partial differential equation was the trigonometric function, just the linear superposition cosine and sine function. And by this boundary condition, this field should have the following unique solution. Okay, cosine and cosine for TE mode. Furthermore, another boundary condition on the third and fourth surface, this beta x and beta y eigenvalues of this function should take the form of integer m times pi over a, purely related to just the geometric parameter of this cross-section. Also, beta y is the integer n times pi over b, okay, the vertical dimension. So this beta and beta x and beta y determines the cutoff frequency that allows wave to be propagating inside this waveguide. The cutoff frequency was the speed of light times square root of the this beta x squared and beta y squared. And this cutoff frequency can change depending on integer m and n. So TE mode's case, these integers start from 0, but the mode when m and n both are 0 was not the solution of our interest. So that the mode which has the lowest lowest cutoff frequency correspond to m is equal to 1 and n is equal to 0. That's because it is customary to assume that the lateral dimension A is larger than B. The opposite case, lateral dimension is shorter than the vertical dimension, then the lowest mode would be TE01 mode. Okay, you can investigate inside of this square root, resulting in the value of the cutoff frequency. Okay. Actually, it was cosine and cosine. This can be interpreted through the bouncing wave picture. That's because by Euler formula, this cosine can be expanded by some of the exponential function, which correspond to traveling waves. Okay. So for various m and n indices, we can figure out the cutoff frequency of each mode. Again, the lowest mode was TE01 mode. And the other case that we have discussed was circular waveguide. We transformed this transverse Helmholtz equation to that in the cylindrical coordinate system. In that case, the general solution was the Bessel function, okay? But due to the boundary condition, the solution should be the Bessel function of the first kind. And this TEZ mode case, this eigenvalue, beta S, can be determined by inspecting the zero crossing of the derivative of Bessel function. All the zero crossing information is included in this table. We can use this table to evaluate the cutoff frequency of the TE or TM mode of the circular waveguide through this cutoff frequency equation. Cutoff frequency directly depends on the zero crossing value of this Bessel function. And because this 1.8 for 1 zero crossing value when n is equal to 1 and m is equal to 1 is the lowest value. This is the lowest mode that circular waveguide support. So using this transverse field profile that we have obtained, we can evaluate the whole field component, electric and magnetic field, by using Maxwell's equations. If we draw the this transverse field profile, then yeah, we can intuitively understand their behaviors. But due to the finite value of conductance of the waveguide, there should be metallic or ohmic loss. This ohmic loss comes from this tangential magnetic field. So in order to minimize loss, we need to find mode that has the lowest value of the tangential magnetic field. That was the TE01 mode. You can see in this figure, as frequency increases, the loss is lowest among all the other modes. And also there is another strategy to reduce this loss by using corrugations used in horn antenna. And also we have talked about the Quasi-Tem mode. Actually, this microstrip line consisting of two metallic structures insulated by this dielectric material, but above there's air. Pure TEM mode cannot be supported due to the phase mismatching. But this microstrip line operate very, very low frequency, so that the extent of this phase mismatching is very small, so that this longitudinal field are also very small, so that it almost looks like TEM mode. In that case, we can apply the transmission line theory that we have studied before. So this is all. So yeah, by the way, there is office hour after, starting from 3 p.m. So you can join and ask any questions to TA GAG. Okay. Are there any questions? Otherwise, we can stop here.
Could you please explain again for this Quasi-Tem mode? What is the phase mismatching? How does it happen here?
Yeah. So by the way, the wave is propagating to the direction perpendicular to this paper, on this paper, right? So if this is not the electric material, if this is air, then the material property in this region and in this region the same, so that the propagation constant is going to be omega mu naught epsilon naught, omega mu naught epsilon naught. So it's going to be beta z and beta z of wave propagating this above region and the region in between these two metallic structures. So because media are same, so their propagation constant are same. But if we introduce the electric medium, which has a different medium property to the air, so that the propagation constant beta z in this region is going to be omega mu 1 epsilon 1, so that the propagation constant in the free space or air is different. This and this are different, so that the phase, at this interface, there should be phase mismatching. That means that pure TEM wave, different regions cannot be supported. But the field take the very complicated form such that phase is matched and all the boundary conditions are satisfied. And that is kind of appearance of the longitudinal component, but this task, to have the closed form of this longitudinal component and all the exact solution of this microstrip line is very complicated. We need to use some numerical method to find the exact solution, but it's just a kind of proof why TEM mode cannot be supported, this microstrip, due to the phase mismatching.
Okay, I see. Thank you.
Mm-hmm. Yeah, then we can stop here. Thank you very much, and see you later.
Thank you.
Thank you.
Thank you.
Thank you.